just buy separate tickets or like some sort of subscription? Uh-huh. Oh, really? No, I don't think we've been there. We've been to the Musical Academy to see one show, but honestly, I don't know. I didn't think it was that great. No, it was just like a show, like the Matilda, I think. And I see. Yeah, I mean, like we didn't really go before, and now like last weekend we saw the building and yeah, I mean. They also have yeah, yeah, it might be nice. I mean, I like music, and she used to play piano. I mean, so she has a little bit of, like, it was a long time ago, but she has some musical background, so maybe it would be interesting. Yeah, there's a lot of famous musicians. How is the orchestra, like, Philip? Or they're the top four. Oh, really? Oh, wow. Interesting. That's pretty cool. Yeah.
It is known for string. Chicago's for brass.
Oh, really? Huh. Interesting that they would like specialize kind of.
Conductor, all the famous engineers.
I see. Huh. No, the reason we went, there was this show, well, we told you like Hamilton, and everybody's crazy about it, and we saw that it's coming to Philly, so yeah, trying to figure out how to get in.
Okay, so I'll make a quick introduction. Okay, so welcome to this week's GRASP seminar. So we are, this semester when I sent out a request, a lot of requests came back saying you guys want to hear about deep learning. And this is a very sensitive topic because some people hate it, some people like it. Some of you out there are, probably didn't want to hear about this word. But it's taking over many conferences and many areas. Areas moving very fast. So every day, every week, there's a new result coming through. So if you're not on top of it, it's okay. You have time to chase up because everybody will be chasing at the same time. So this semester we're having quite a few outside speakers come in to give a talk on this area. And I thought it would be good actually to preview some of the work done here at Penn. So we have very fortunate to have some of our graduates who are leading efforts. So we're going to start with Gedas, and then Carlos and George is over there. Great. Okay. So feel free to ask questions and
Okay, so today I'll present our recent work on human behavior understanding using first-person cameras, which is joint work with my collaborators Hyun-Soo Park, Stella Yu, and John Bushi. And so I'll start with a brief introduction, brief discussion on some of the recent technological trends. So if you look at some of the recent technology media or even shopping websites such as Amazon, you can see it becomes very obvious that this concept of a personal AI assistant is becoming more and more popular, and more people in the industry are working on it. And so I'll start with this because our work is slightly relevant to this idea. And so if you look at some of these devices that are currently being developed or already in the market, most of them are based on third-person cameras. So maybe cameras installed somewhere in the house or directly deployed on the robot. And so in our work, we propose to use first-person cameras for this task for the following reasons. So imagine now we have a scenario where people are maybe trying to cook some dish. And so in this case, we would want this personal AI assistant maybe to give some sort of useful recipes or some sort of other information to these people to make their daily tasks easier to accomplish. And so in order to do so, in this case, it needs to be able to understand what exactly this person is doing. So what kind of dish is he or she making, and other subtle nuances of his task. And so if you look at the first person, if you look from the third person perspective, it's actually pretty difficult to do so because the distance between a third person camera and the person is quite large, and the number of informative pixels is very small, which makes it much harder to understand what exactly this person is doing. And so that's why we use first-person cameras, because now the first-person perspective allows us to see exactly what the person sees, and you can see that the number of informative pixels becomes much larger, which allows us to understand that person's behavior with much higher accuracy. And so now, once we figured this issue, now we essentially have a means to obtain as much informative information as possible. Now we really want to get into some of the more subtle details behind this personal AI assistant, and specifically what kind of characteristics it should have. So probably the first thing that we wanted to have is that we wanted to understand what the person is currently paying attention to. And so then it could be able to use this attention mechanism to recognize some sort of activities that that person is performing, and then give feedback specific to those activities. And so if we take one step even further, maybe we want to incorporate a possibility of this personal AI assistant to identify how good this person is at a certain activity, and maybe give some sort of suggestions how to become better at this activity. And finally, for this assistant to be truly autonomous, we also wanted to be able to infer what the person will do next and kind of anticipate this person's needs before they even arise. And so this would be a particularly useful characteristic. And so now I'll talk about each of these points one by one and try to relate some of our work to these points and how we're trying to achieve these goals. And so obviously we're going to use first-person perspective to achieve all of these goals. So first, let us focus on this idea of trying to make this device to try to understand what the person is currently paying attention to. And so to investigate this task, we define the concept of action objects. So these are basically objects that capture a person's conscious, tactile, or visual interactions during an activity. And so then our goal is to detect these action objects from first-person RGBD data, as shown here. And so the key question is, how do we do this? So we know that certain objects are more likely to attract person's visual attention, and we also know that a person is more likely to interact with objects that he or she can physically reach. And so inspired by these observations, we propose to detect action objects using visual semantics and 3D spatial cues. So the visual semantics are encoded in the first-person RGB image, and we encode the 3D spatial semantics in a DHG image, which is a concatenation of depth, height, and grayscale images. And in addition, we also want to incorporate a spatial 2D prior, because the way a person positions himself relative to an object affects the location where this object is mapped in the first-person image. So for example, in this case, we have two laptops, but only one of them is an action object. And both laptops have very similar visual appearance features, but they appear in different spatial locations in the first-person images. And so we want to incorporate this XY coordinate grids as additional features to detect action objects. So now we propose our EgoNet model, which is a two-stream fully convolutional network that detects action objects. And so initially we feed the RGB and DHG images through two separate convolutional pathways. The RGB pathway learns visual appearance features, while the DHG pathway learns 3D spatial features indicative of action objects. And then the joint pathway is used to concatenate the FC7 features from both pathways together, along with the XY coordinate mesh grids, as shown here, and then we feed this concatenated representation through another convolutional layer. And so this allows us to essentially blend visual and spatial features together and learn an action object-specific spatial distribution. And the entire network is then trained jointly end-to-end using this per pixel cross-entropy loss function. And so if we look at the results now, you can see that our method is able to accurately detect action objects in a lot of different environments, and regardless of the object classes, which is exactly the behavior that we want. But one of the problems with this approach is that it's fully supervised, and meaning that we need a per pixel action object annotations to train this network, which are very costly and time consuming to obtain. And so our next goal is to try to learn these action objects without using these annotations. And so to do this, we propose to model this action object detection problem as an interplay between recognition and segmentation agents. And so intuitively, the segmentation agent will first propose a candidate action object segmentation mask, which a recognition agent will then use as a supervisory signal to try to learn action objects based on visual and spatial features. And so this will then allow us to learn to both recognize action objects and segment them out of an image. And so now we implement a segmentation agent using this MSG projection scheme. So basically what we do is this MSG projection scheme, it takes two inputs, a coarse action object mask and the segments generated by some unsupervised method. And essentially what we're trying to do is then we're trying to project this coarse action object mask on these regions to get, on these segments to get this sharp action object segmentation mask as shown here. And the recognition agents are implemented as a two-pathway fully convolutional network where we have the visual pathway that tries to recognize action objects based on what they look like, and the spatial pathway tries to recognize action objects based on where they are in the first-person image. And so the visual pathway is implemented as a standard fully convolutional network, while the spatial pathway has this additional location-dependent layer which allows us to learn action object spatial distribution. So now the question is, how do we incorporate all of these components together? So we have our two pathways, and we have a bunch of unlabeled first-person images that we want to use to train our network. And so we propose to do this using alternating cross-pathway supervision. So essentially what happens is that we know that this first-person data has a very strong spatial prior, meaning that people typically position themselves in a very consistent way relative to an object. So initially we simply guess where we expect this action object to be. We put a Gaussian around this guess, and then we feed these Gaussians through our segmentation agent, which gives us these segmentation masks that are used to supervise the visual pathway. And so the visual pathway then tries to learn some of the basic characteristics that describe what these action objects look like. And so of course these masks are pretty noisy, and they don't capture everything accurately, but we're hoping that there's some pattern that the visual pathway will be able to extract. And so during the second round, then, we feed the predictions from the visual pathway, which are now better, as you can see, through the segmentation agent, which gives us improved segmentation masks, and then we use them to supervise the spatial pathway. And so we keep doing this until both pathways get better, and also as the segmentation agent gets better as well, and until we get pretty much no improvement in the accuracy. And so this is basically usually done in 3 or 4 iterations here. And so now if we look at the results, we can see that our method, despite not using any annotated data, we can actually outperform a lot of supervised methods, which is very surprising. And so the reason why this is happening is, as I said, our method only uses unlabeled data, which is very cheap and easy to obtain. We can simply go to YouTube and download a bunch of first-person videos, whereas the supervised methods are constrained by the amount of labeled data that there is, and especially with first-person data sets, these data sets are very limited. So basically, our method can use any amount of unlabeled data to train it, which is beneficial, and that's why we outperform these other methods. And if we look at the quality of the results, you can also see that we actually get very solid predictions here, and in many cases, we even outperform our previous method, EgoNet, which was supervised. And so now we talked about these 4 points. So now if we want to use these action objects for activity recognition, if we look at these predicted action objects, we can see that even just looking at a small region around these objects already tells us a lot of information, what this person is doing. And so this really, when we have a limited amount of training data, this really makes it much easier for the network to learn these activities. And so these action objects are very useful for this task. So now I'll switch gears a little bit and talk about the third point, how to identifying how good a person is at a particular activity. And so in this case, we will look at the basketball activity from the first-person perspective, where we have people wearing first-person cameras and recording their game. And we can essentially see exactly what this person sees during the game. And so the question is then, well, can we understand how good this player is just from his first-person video? And so due to time constraints, I'm not going to go through a very detailed explanation, but the short answer is yes. And the way we're going to do this, essentially we can learn this performance assessment model as follows. So what we do is we take a pair of first-person basketball videos as an input with a label indicating which of the two players is better. And we can then use deep learning to construct very powerful visual spatiotemporal features And then essentially using these features, we add some extra parameters, and we can pose this problem as a hinge loss minimization problem. And so essentially our model, it tries to, at every iteration, it tries to predict which of the two videos, which of the two players is better. And so it turns out that we can do it pretty accurately. And so now, given some testing data, where essentially a pair of two first-person videos, we can correctly predict which of the players is better with about 77% accuracy, which is pretty solid. And the nice thing about this, that not only do we get some number representing how good this person is, but we get these qualitative results, basically the positive and negative events associated with this player, which gives us a much more intuitive understanding what this model is actually doing and how it's reasoning about whether the person is good or not good. And so here is a bunch of examples of positive events that were detected as a byproduct of this performance assessment training. And so now, as a final task, we talked about that it would be very useful for this device to infer what the person will do next. And so once again, here we stick with the same basketball example. Now our goal is to try to predict which of the players the person who's wearing the camera will cooperate in the future, so maybe 2-3 seconds from now. And so ideally, we also want to learn this, to solve this task without using any annotated data. And so the way we're going to do it, we will use this so-called cross-model EgoSupervision scheme. So we will take a pre-trained multi-person pose estimation network, which already outputs, which detects all the people in the scene along with their pose. And essentially then what we can observe is that we can, because this data is the first-person data, we can transform these outputs to incorporate these certain first-person characteristics such as egocentric spatial prior, size prior, and pose prior. And so it turns out that this transformed output can be used as a very effective supervisory signal. And so then what happens is we can transfer the knowledge from this pre-trained network that then it outputs some pose predictions and the person predictions. Then we can transform this output using this so-called ego transformer. And then this transformed output is used as a supervisory signal for our cooperative intention network. So we're essentially transferring knowledge from this pre-trained network to the network that we want to train. And so if we look at some of the results, we can see that we can actually predict pretty well with who this person who's wearing the camera will cooperate in a few seconds. And so obviously this is a pretty difficult task, and even for humans, they're not able to solve this with 100% accuracy. And so our method achieves about 80% accuracy, and the humans, they achieve about 90% accuracy. So there's still some room for improvement. And so to conclude, I think, so the key takeaway here is that the first-person data is very well suited for analyzing human behavior. And so we showed that we can reason about person's attention, intentions, how good that person is at a particular activity, what kind of activities is that person performing. And so that's really useful when we think about these higher level applications, such as developing personal AI assistant. And also one nice thing about this first-person data, that in a sense it provides us implicit labeling. So what happens is that by performing activities and by looking at things, the person is implicitly labeling what's important to him. And so this is very nice, because now we can use this sort of implicit labeling to train these deep networks in an unsupervised fashion, which is very nice, because for a lot of, especially if you have a per pixel prediction task, getting annotations is very difficult and time consuming. And the final key takeaway is obviously that the deep learning, in this case, all of the methods are based on deep learning, and it provides if you have enough data, even if it's not labeled, it provides a very powerful framework to solve these new computer vision tasks. Yeah, so that's all I had. And if you have any questions, maybe we have time for one question. Is it this one?
I tried that.
I think you need to unplug that.
This is the what this?
The cable was here. No, but it's not my
Which cable is this? The cable? How about this? Do you have another connection? Oh yeah, okay, go here. Yeah. Let's try this one. So can you set up?
Maybe George can do it first.
George,
and I'll
can you
yeah.
come up first? Yeah, maybe this thing disconnect.
20 minutes ago.
Go ahead first, yeah. Then maybe transfer your stuff to the dongle.
Yeah, I'll send it.
Sorry. Okay, great. Sorry about the delay.
Hi, I'm Georgios Pavlakos. I am a fourth-year PhD student here working at Penn, and I'm lucky enough to be advised by Kostas, which also means that I'm working under the GRASP lab. And today I would like to present our work on 3D human pose estimation from a single image using convolutional networks with coarse-to-fine volumetric prediction. So this work was presented earlier this year in this VPR. So since the emergence of deep learning, the whole field of computer vision has completely transformed. In particular, for 2D image understanding tasks, these deep networks have been very effective. And in fact, Gedas that talked earlier has done some fundamental work in these 2D tasks using deep networks. So, however, when we are going to do the transition from 2D tasks to 3D tasks, well, this transition has been much more challenging than what we expected. And this is challenging because first we need to answer some questions before we do this transition. So first we need to decide about what representation we are going to use. For images, this is standard. Okay, we are using pixels, but for 3D data, do we want a depth map? Do we want maybe a mesh representation, a voxel space, or a point cloud of an object? And apart from that, how are we going to reach at high resolutions for 3D data? Because deep networks are known that it is known that they don't scale very well when we reach higher resolutions, and these problems escalates very quickly when we are going to 3D. So we might want to use a more efficient or a more effective representation for 3D data like an octree. And finally, on top of all that, we have the issue of training data. So the whole revolution of deep learning can, at least in part, be attributed to the availability of huge data sets. And for 2D images, this is easy to have humans annotate 2D properties of images, but for 3D, this is much harder, and our benchmarks are usually much smaller, and we don't have this large availability of data that we can train with. So how are we going to deal with these problems? Are we going to just like abandon any try of using deep learning for 3D tasks? Well, not really. The world that we are living is three-dimensional, and we do want our sensors to perceive this extra dimension as humans do. So, and this is particularly true for us working in robotics. So if we have a grasping robot, for example, we do want to have the robot to perceive the 3D pose of the object such that we can also enable the grasping. And this is a video from a recent ICRA paper this year. And another use case is when we're having a quadrotor that is following a human. We want this finer level representation of 3D pose and understanding of 3D pose such that we can also enable the interaction between the human and the quadrotor. So the answer is yes, we do want to use deep learning for 3D tasks, and we want to make it effective. And for the rest of the talk, let me focus on this problem of 3D human pose estimation, which is a quite fundamental and typical task of 3D understanding from images. So the main goal of the task is, given a single color image of a person, we want to estimate its full body 3D pose, where here we represent the pose as a set of 3D coordinates for the most important body joints, like X, Y, Z for elbows and for shoulders and so on. And a traditional pipeline for this approach, for this problem, is offered by reconstruction approaches, which our lab has also been very active in working in this area. And the main idea is that for reconstruction approaches is that we are given an image of a human, we are using a discriminative approach to estimate the 2D pose on the image, which is just pixel locations of the joints on the image, and then using some model, which effectively expresses our understanding about the 3D scale, the 3D representation of the human body. We can lift these 2D estimates to 3D by solving an optimization problem. So this is how typically this problem has been approached, combining a discriminative approach to estimate the 2D pose. Here it is a deep network, it doesn't have to be one, but it just happens to be the most effective for this task. And then using a model-based, optimization-based approach to resolve to lift the 2D estimates to 3D. And as I said, our group has also published on this paradigm, and I'm lucky enough to be involved in one of these works. And this, in fact, works very well. It is, works for many different actions, for many different backgrounds and humans, so it is quite robust. However, the main problem of this paradigm is that it has to deal with a reconstruction ambiguity, which means that even when the 2D prediction is perfect, the estimated 3D pose can still be erroneous. And this is because this model here only observes the 2D locations of the joints. So there is some ambiguity when we are doing the lifting to 3D. And while here a human can see that the left leg is closer to the camera than the right one, the model cannot resolve this ambiguity. So ideally, we would want to take advantage of image cues such that we can resolve 3D ambiguities. And a very good candidate to process image information is, of course, deep learning. So a very straightforward approach is to use the deep network, like use deep learning as a generic function approximation tool, which takes an image as input and spits out the 3D pose of the human, where here the most naive way to represent the pose is just as the 3D coordinates, x, y, z location of the joints. However, the problem with this very naive approach is that the mapping from images to 3D coordinates directly is very hard to learn for the network and makes the task highly nonlinear, which also creates, has the issue that makes this approach underperform compared to the previous pipeline. So how are we going to solve this, this issue here, that deep learning seems to not work very well for our 3D task? First, thinking back about the problems that we identified with deep learning in 3D, first we're going to fix the representation. So for our work, we introduced the volumetric representation for 3D human pose. Effectively, we discretize the space around the subject and we predict per voxel likelihoods for each joint in the space. So instead of 3D coordinates, our network regresses 3D heat maps or 3D probability, 3D likelihood maps for each joint in this 3D space. And this representation has actually some major advantages compared to coordinate regression. So first, yes. So first, the mapping from images to 3D volumes is easier than images to 3D coordinates and more intuitive for the network because each pixel effectively corresponds to a series of voxels instead of having to learn a mapping from all the pixel values directly to the XYZ coordinates. So we make the mapping from the network for the network easier to learn. And on top of that, we also are able to use a fully convolutional network for the prediction. So we only learn convolutional filters to map from the image to the 3D volume. While for the coordinate regression approach, we need to have some fully connected layers, which usually increase the number of parameters for the network. And because we need to learn, for each output, we need to learn one weight for every pixel that we want to correlate. And finally, our representation, our 3D representation, is much more informative than just XYZ coordinates because it can be multimodal. We can treat it as a generic probability distribution and can use it for other tasks or for post-processing, like enforcing structural constraints or enforcing temporal coherency if we have a video that we process. So first, with this change in the representation, we can get some critical advantage for our approach. But still, we have here we predict a 64 by 64 by 64 cube for each joint, for every joint individually. So we need some high resolution for the prediction. And we also need to address the resolution issue that I presented earlier. So how we're dealing with that? What has been typical for deep networks recently is, for at least for some specific problems, is that people are using iterative prediction, which effectively means that they want to use deeper networks and they have one prediction at the early stage of the processing and then use another network component which refines this prediction and another one until the most refined version at the end of the pipeline. So we could use this scheme and just change this intermediate output with our 3D representation. However, because of its high dimensionality, as I said, 64 by 64 by 64 for each joint, which for 17 joints might mean a few million parameters here, this explodes very easily and gives us only diminishing returns. So instead of this naive iterative prediction, we are using a coarse-to-fine prediction scheme. So in detail, we increase the resolution for the most challenging Z dimension of the output volume, effectively for the unobserved depth, for the dimension that is lost during the projection. For this dimension, we increase the resolution gradually during the processing. So at the early stages, we might have just a very coarse prediction for depth, even just 2D, no depth in our prediction, which is then refined and refined and refined until the end of the pipeline, where all the information has been processed and consolidated, and we can get the most accurate prediction in a very high resolution. So with this approach with changing the representation and changing the prediction scheme, we can get very important increase in the standard benchmarks like human EVA and the most recent human 3.6 million dataset. And we can achieve more than 30% relative error reduction compared to previous approaches, both discriminative and hybrid approaches as the reconstruction approaches. So this is very nice, but still we have the problem, the issue with the data. Do we need training? We need images with corresponding 3D ground truth to train this network end to end. How can we relax? Is there any possibility that we can relax this constraint? In this case, if these data are not available for training, we are inspired by reconstruction approaches, and instead of training the network end-to-end, we propose first to train a component which recovers only the 2D pose. So for this part, we do have a lot of annotations on image, because humans have annotated 2D joints on images, so we can train this first component very effectively. And then we train a second network component, which is trained only on mockup data, so only geometric 3D data from mockup data acquisition. We don't need any image correspondence for this part. And we can train this one very effectively, this network component very effectively, which effectively learns to lift, given a 2D pose, to predict a plausible 3D pose here. And when we combine both components together, we can go from image directly to 3D and have this network working very well also for in the wild examples as the ones here, where usually we don't have 3D ground truth for these generic images that we can find maybe on the web. So this indeed is a very appealing approach to deal with the problem, and possibly more generic. But still, if you have the data to train the network end-to-end, so if you do have images with corresponding 3D ground truth for training, of course you can achieve much better result. So this is what we recommend to do. So let me conclude here by giving some takeaway messages from this talk. First, when we're going to 3D, a major factor is to decide on the representation, and here we saw that by using volumetric representation for 3D human pose, we could get big improvements in the performance of the network. Second, you have to think about how you're going to reach high resolution predictions and possibly more accurate predictions. And here we employed a coarse to fine prediction scheme to allow us to get high resolution 3D predictions. And finally, if you don't have the data for training, there is always this decoupled approach. First solve the 2D problem and then solve the 3D problem independently, which is more generic but still underperforms compared to just using, just solving the 3D problem directly from the image. So yeah, we also have a project page where you can find training and testing code for our approach. And if you have any question, I would be happy to answer. Thank you. It's usually on the person, and looking at the features as well, you can see that without using any segmentation, the network, some of the feature maps are effectively segmentation feature maps. So it can, it constrains the person as well. So it learns to constrain the person as well. It's not as good as using actual segmentation ground truth, but this is an intermediate response we get from training with 3D ground truth for pose.
So the introduction techniques is an assumption as to what a person looks like, the proportions and everything. Does this still make that assumption, or are all the joints independent?
All the joints are independent. So that's why I mentioned at some point that you have this 3D ground truth, like this 3D heat map, which you can use later to enforce some special constraints on the human body. We only use whatever the network learns. We don't have any particular constraints on the human body here.
Do you know if the network's learning are meeting those constraints, or if I had somebody who had like a half-length limb, if we would be able to handle that? Okay.
I think if it hasn't seen such an example, like you mean just like a
So
link.
if you have someone who's disabled, who has like a partially developed limb, they still have a shoulder, an elbow, and a wrist, would it be able to pick those up okay, or will it say, oh, that's not real?
It will probably, I mean, it will probably guess a good prediction for what for the training examples, from the training examples that it has seen. So it will probably position the hand somewhere that would be feasible for this case. But it will be with very low confidence because you have this heat map response, like this probability distribution. It will probably fire somewhere, but with very low response.
Keep the single on top.
Good morning. Sorry for the delay before. I'm Carlos, and I'll present the Polar Transformer Networks, which is a work with Christine, Jaue, and Professor Costas Danilidis. So we seek to understand the effects of geometric transformations in deep neural networks. So for instance, if you want to classify handwritten digits, but these handwritten digits can come in any orientation and scale and in any part of a bigger image. We want to understand how these affects, how these transformations affect the classification performance, and what can we do to improve the performance when we are subject to these kinds of transformations. So first, let's define what invariance means. We say that a function f is invariant to some class of transformations if the input is subject to a transformation from that class, the output doesn't change. So for instance, that's what we want in a classification problem. The image here is showing a rotated version of a digit, and we want the class to be the same. And we know that given enough data and capacity, CNNs can learn some degree of invariance. However, your training set must contain lots of transformed data in order for the CNN to be able to learn this invariance. Okay, so if you want to classify rotated images, we want to give the conventional CNNs lots of rotated examples. So what about translations? Does it make sense to give translated versions of the input for the CNN? To answer that question, first we need to define equivariance. And I will start with the simplest definition, which is translational equivariance. So if you imagine that the function f is learning some some key points of the silhouette, we say that f is translational equivariant. If we do a translation on the input, the result is the same translation on the output. The concept is a bit more general because the transformations p and pi and psi don't need to be the same. They don't need to be translations. And we see in our case, pi will be a rotation and a scaling, and the psi will become a translation, and it's still equivariant. So now to answer my first question, we don't need to do translation augmentation on convolutional neural networks because planar convolution is equivariant to translation. Then we can see some examples. I'm translating this digit along the image, and I'm computing the convolution with some edge detecting kernel. and the result of the convolution is doing the same translation as the input is. So we don't need to augment a CNN with translated versions. And okay, I've said that convolution, the planar convolution is equivalent to translation, but we need to show that the convolutional feature maps of CNNs are equivariant, which we can show because the nonlinearities that are present on CNN are pointwise, so they preserve equivariance. And the pooling operation gives some sort of local invariance when you do max pooling to reduce dimensionality. And if you do a global average pooling, as we usually do in the final convolutional layer, we are actually transforming that equivariant feature map in an invariant image descriptor. So, okay, we are equivalent to translation, but what about equivalence to other transformations? We can show that the planar convolution is not equivalent to rotation. So in this image, I want you to look at the first and the third column. We have a rotated version of our input here, and we're computing convolution with the same filter, and we see that the output of the convolution is not the rotated version of the convolution with the original image. So we do not have rotation equivariance in planar convolutions, and so we do not have rotation equivariance in convolutional neural networks. So what this means for CNNs is that we don't have a shortcut. We don't have an easy way to deal with rotations. The CNN must waste capacity and requires more data to be able to handle these kinds of rotations. And then we conjecture that if we come up with a rotodilation equivariant representation, we can achieve improved performance in problems where the inputs come at different scales and rotations. So now we'll talk about previous work on this, on dealing with input transformations. So a very important work is the spatial transformer networks. So they are dealing with affine transforms of the input, and they deal with this problem by trying to predict a transformation that learns a canonical orientation of their inputs. So they do that, they do this differentiable sampling so they can train all these things end to end, but they need to do a regression on parameters of an affine transform, which is very hard to learn. And then it turns out the spatial transformer works well with mild deformations if you have a lot of data. So another important work is the harmonic networks. It's a completely different approach. So instead of trying to transform the input, they draw their filters from an equivariant space. So they design these radially symmetric complex filters in such a way that if you have a rotation of the input, here this thing is in polar coordinates, so if you have a rotation of the input, the result of our convolution will result in just a change of phase of your complex value of the convolution. So if you take the modulus of these complex numbers, you'll become invariant to translations. So the harmonic networks are not equivalent to dilations. They can only handle the rotation problem with these filters. And they need to reduce, they need to restrict their filters, so they lose expressivity. Their filters must be constrained to be radially symmetric, which is a big constraint. And they have to do complex convolutions, which are 4 times lower than a conventional convolution. Then we have to talk about this other approach called the TI pooling. It's transformation invariant pooling. So this is kind of a brute force approach to transformation invariant. What they do is they make copies of the inputs subject to all the transformations that you want to be invariant to, and you run all those copies through the network and do a max pooling at the end on the learned feature representations. So since the max is an operation that doesn't depend on the order, you achieve invariance. If invariance to whatever transformations you did in the first place. The problem with this is that it's much slower than a conventional approach because you have to pass this image through the network up to 24 times, just rotating 15 by 15 degrees and send all inputs to the network. However, this is the state of the art in the rotated MNIST, which is a data set we're dealing with. Okay, now we start to talk about our contributions. We start with some theoretical background. So we can define a group equivariance a function phi is equivariant to transformations from the group G if this holds, so if you can commute the transformation with the application of the function. And we also can define a group convolution where we are doing convolution over the elements of the group G. So you can see this as sort of a dot product by applying, if you have a filter F, we apply all possible transformations from that group to F and do a dot product with your input. This is sort of intuition for the group convolution. And then we can prove that group convolution is equivariant. So if I'm drawing transformation from a group and if I'm doing the convolution on that group, I have an equivariant representation. And then a particular case of that is what we are used to, which is the planar convolutions. They are equivariant in the group of translations on the plane, which is what we use all the time in CNNs. But what we want for this project is equivariance in the group of rotodilations. So we have a group of rotations and dilations of the inputs, and so we want to solve this. If you can represent our feature maps using this convolution on this group, we will have an equivariant representation. The problem is how to compute this convolution. And the solution to the problem is a change of coordinates. So in canonical coordinates, we can parameterize the image with r and theta, so with a distance to an origin in an orientation. And then we can show that the argument of the filter here, which is the application of a rotodilation to the coordinates, becomes a translation in the polar, log polar representation. So it turns out that this convolution becomes a regular planar convolution, which is what we're used to, and which means that if we do this transformation, we can use a regular CNNs to classify or to other tasks which involve rotations and dilations. So this is to visualize the example. So in the first row, we are rotating this digit, and in the second row, we have the corresponding polar images. And we can see that the rotation here becomes a vertical shift in the polar image. And here we are applying scalings, and we see that the scaling here becomes a horizontal shift on the polar images. So this is an equivariant representation. However, when we do that, we lose translational equivariance. So on this figure here, I'm showing a polar transforms of this image here taken at different origins. So, and the origins just a few pixels apart, but the polar images are very different because we lose translation equivariance. So a minor translation may result in a completely different polar image. So we have a problem how to choose where to put the polar image, the polar origin, sorry. So if we can choose the origin consistently, we achieve translation invariance. So, and what we do is we learn it. So we predict the origins as the center of a feature map at the end of a sequence of convolutional layers. And yeah, that's how we get the origin. Then the problem is we don't have supervision for what a good polar origin would be. So we want to train everything end to end. And then we need everything to be differentiable. And now we are inspired by the spatial transformer networks. Where that's what they do. They learn parameters of transformation, they have a grid, and they can do the interpolation and the sampling in a differentiable way. So we use their sampler, and what we need to change is the grid. So we have a polar grid, it has no parameters here, and the only parameter that we need to learn is the centroid. So we're just, our regression is just regressing two coordinates, and since we regress these coordinates to the center of a feature map, that's very easy to learn, as opposed to the affine transform on the spatial transformer that needs to learn entries on a affine matrix. So now, after the polar transformer, we have a polar image. So rotodilation of the inputs will become translations of our polar representation. And now we can apply as many as convolutional layers as we want, and we're still maintaining equivariance up to the last convolutional feature map. So our final convolutional feature map is translational invariant and rotodilation equivariant. And this is to prove what I just said. These are feature maps on the last layer of a network. So if you look at the first and the third rows, we have a translation, and you can see that the feature maps barely change. This shows that we are invariant to translation. If you look at the first and the second rows, we have a rotation of 180 degrees. So the feature maps should shift half width in the vertical direction, and this is what we see here. And if you look at the first and the fourth row, the difference is scaling. So we should see a horizontal shift. It is what we see on the feature maps. Okay, so these are our results in the rotated MNIST 12K, which is a popular data set for people who study rotation invariance. So the top 4 are variations of our method. All of them improve upon the state of the art, which is the TI pooling. And in particular, I want you to compare the second row with the TI pooling, where we use almost an order of magnitude fewer parameters and almost 10 times faster, and we reduce their error by more than 20%. So, but we can say that the rotated MNIST is an easy data set. So we introduce a SIM2 MNIST, which has distortions of rotation, scale, and translation. So it's more challenging, and in that data set we do much better than all the other methods tried. So we extend our method to 3D object classification. So this is the ModelNet data set, and they have rotations, they have 3D models rotated about the z-axis. So we do a cylindrical transform on the z-axis, which means we are kind of repeating the polar transformer at every slice along the z-axis. So if you look at the first and the second rows here, we are rotating this chair, and this is our representation of the cylindrical transformer. We see that rotations here becomes shifts on this representation. And then if we use a 3D CNN to classify this object, the 3D CNN will inherit the translation equivariance, which will become rotation equivariance for this case, and we hope to get better performance with that. So this is our results on modern F40. We are not state-of-the-art, but we are competitive. We got 89%. The state-of-the-art is 91.4. Okay, now that we are talking object classification, I'll talk about our current work. So we are exploring equivariance in SO3. So we've showed that group convolution is equivariant. So if you can compute the convolution in SO3, we'll have equivariant representations. Representations equivariant to 3D rotations. So the way we do this is mapping our functions to the unit sphere so that we can efficiently compute the SO3 convolutions by expanding those functions in the spherical harmonics and applying the convolution theorem of the spherical harmonics, which is the counterpart of the convolution theorem for Fourier transforms. So if we expand in spherical harmonics, we can do pointwise multiplication of coefficients on the spherical harmonics to compute this convolution. So we are building a spherical CNN because we know how to compute the group convolution on SO3 on spheres. And this is some examples of feature maps. So these on the left side are chairs. I don't know if you can see them. So I want to show that these feature maps are equivariant. So if you look at this one, the legs are kind of pointing towards us, and we have some feature maps that activate on the legs, like this third one and this fifth one here. So we can see the 4 legs here, and here we have another chair that's pointing directly towards us. We can see the legs activated here, and yeah, if you make an effort, you can see that we actually achieve an equivariant representation to 3D rotations. So to conclude, we propose a network invariant to translations and equivariant to the groups of relations and rotations. We improve the state of the art on the rotated MNIST significantly. And we have code available. If you want, check it out. Thank you. What do you mean by
When you do a
resolution?
polar transform, sampling rate at the further away.
Oh, I see. So the cells are larger than the center, right? Yeah, so we kind of don't care about it because our representation is equivariant anyways.